Apart from classifying elements into S, P, D, and F blocks, the periodic table also shows the classification of elements into metals, non-metals, and metalloids. Metals have been listed on the left side of the table and form 78% of the known elements. Metals generally exist as solids at room temperature. An exception is mercury, which is liquid at room temperature. Metals usually have high melting and boiling points. With the exception of gallium and cesium, which have very low melting points of 303 Kelvin and 302 Kelvin respectively. Metals are good conductors of heat and electricity. Metals are malleable, that is, they can be flattened into thin sheets, and are ductile, which means they can be drawn into wires. These properties are in direct contrast to those exhibited by the non-metals that are placed on the top right side of the periodic table. Non-metals are usually solids or gases at room temperature with low melting and boiling points. Exceptions are boron and carbon, which have high melting points of 2300 and 3930 degrees Celsius respectively. It is also important to note that bromine is the only non-metal that exists in liquid state at room temperature. They are poor conductors of heat and electricity. Solid non-metals are brittle, non-malleable, and non-ductile. Across a period, as we move from left to right, there is a transition from the metallic behavior to the non-metallic behavior. Elements like silicon, germanium, arsenic, antimony, and tellurium in the P block of the periodic table exhibit properties of both metals and non-metals, and therefore are called semi-metals or metalloids. You are already aware of the periodic trends in the fundamental physical properties such as atomic or ionic radii, ionization enthalpy, and electron gain enthalpy of elements. Let's now see how the periodicity in these properties is related to the periodicity in the chemical reactivity of elements. While moving from left to right in a period, the atomic and ionic radii decreases. As a result, the ionization enthalpies increase and the electron gain enthalpies become more negative across a period. In other words, alkali metals of group 1 have the lowest ionization enthalpies, and halogens of group 17 have the most negative electron gain enthalpies. Low ionization enthalpy, as in the case of alkali metals, means that the elements are willing to give away their most loosely bound electrons. In other words, alkali metals are good reducing agents and are highly reactive in nature. The most negative electron gain enthalpy being attributed to halogens indicates that halogens behave as good oxidizing agents and exhibit high chemical reactivity. This is in contrast to the noble gases that have completely filled outer electronic shells and thus exhibit a positive electron gain enthalpy and the least reactivity. Chemical reactivity is the highest for both alkali metals and halogens. The maximum chemical reactivity at the extreme left of a period among the alkali metals is due to the lowest ionization enthalpy, which enables it to lose an electron that leads to the formation of a cation. On the other hand, the maximum chemical reactivity at the extreme right among halogens is due to the highest electron gain enthalpy, which facilitates an atom to gain an electron, leading to the formation of an anion. This property of forming cations and anions can be related to the oxidizing and reducing behavior of the elements. The chemical reactivity of an element is best shown by its reactions with oxygen and halogens. The alkali metals and halogens show a higher tendency to combine with oxygen as compared to the elements in the center. The oxides formed by the elements on the extreme left of a period are basic, while those formed by the elements on the extreme right are acidic in nature. For example, sodium, a group 1 alkali metal, forms sodium oxide with oxygen, which on reaction with water forms a base called sodium hydroxide, NaOH. In contrast, chlorine, a group 17 halogen, on reaction with oxygen, forms a highly acidic oxide called chlorine heptaoxide, which on reaction with water forms perchloric acid. Oxides formed by elements in the center are either amphoteric, like aluminium oxide, or neutral, like carbon monoxide. Amphoteric oxides can behave both as acids and as bases, depending upon whether they react with a strong base or a strong acid. Neutral oxides, on the other hand, are neither acidic nor basic. The trend of oxides of the third period is observed as from strongly basic to weakly basic to amphoteric to weakly acidic to strongly acidic. Let's now consider the chemical reactivity down a group in the periodic table. The atomic and ionic radii typically increase down a group. As a result, for representative elements, the ionization energies gradually decrease and electron gain enthalpies become less negative down a group. Also, the metallic character increases down the group while the non-metallic character decreases down the group. Therefore, the chemical reactivity increases down a group for alkali and alkaline earth metals, while it decreases for halogens down the group. In the transition metals in the third series of the periodic table, the change in atomic radii is much smaller as compared to those for representative elements across the period. Similarly, the inner transition series 4F and 5F elements show even smaller variation in atomic radii. The ionization enthalpies of the transition and the inner transition elements are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. A gradation in their physical and chemical properties is attributed to the arrangement of elements with respect to their electronic configurations. In this particular module, you will learn about the periodic trends in physical properties such as atomic radius, ionization enthalpy, electron gain enthalpy, and electronegativity. The first important physical property is atomic radius. Atomic radius can be defined as the distance from the center of the nucleus to the point up to which the density of electron cloud is maximum. Measuring the actual atomic radius is a difficult task for two reasons. First, the size of an atom is of the order of 1.2 angstrom, or 1.2 multiplied by 10 to the power of minus 10 meters, which is too small to be precisely measured. Secondly, the electron cloud surrounding an atom does not have a well-defined boundary, which again adversely affects the precision of the measurement. However, it is possible to estimate the radius or size of an atom by knowing the distance between the atoms in a combined state. Depending on the nature of bonding, atomic radii are of three types. They are covalent radius, metallic radius, and van der Waals radius. Let's learn about each of them in detail. Covalent radius is a general term which is used in reference to non-metals. A covalent radius is 1/2 of the distance between the nuclei of two atoms, held together by a covalent bond in a homodiatomic molecule. For example, the internuclear distance between the chlorine atoms in the chlorine molecule is 198 picometers. Therefore, the radius of a chlorine atom is the half of this distance, which is 99 picometers. For metals, we use the term metallic radius. Metallic radius is half the internuclear distance between the centers of the nuclei of two adjacent metal atoms in a metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometers. Therefore, the metallic radius of copper is 128 picometers. Atomic radii of both the types, covalent and metallic, are usually measured by X-ray or by other spectroscopic methods. Let us now see the variation of atomic radii across the periodic table. Generally, atomic radius decreases across a period and increases as we go down a group. The table lists the atomic radii of few elements from the second and third periods of the periodic table. A decrease in atomic size across a period is due to the increasing effective nuclear charge with increase in atomic number. Nuclear charge is the net positive charge experienced by an electron of an atom. The effective nuclear charge varies with the proximity of electrons from the nucleus. This is because electrons in the inner orbitals shield the electrons in the outer orbitals from experiencing the full nuclear charge. For example, the valence electron in cesium is shielded from the nucleus by the inner electrons. As a result, the valence electron experiences a net positive charge that is less than the actual charge. Across a period in the periodic table, as we move from left to right, the nuclear charge increases by 1 unit in each succeeding element, while the principal energy level remains the same. As a result, the effective nuclear charge increases, and the electrons in the valence orbital get more strongly attracted to the nucleus, reducing the size of the atom. Down the group, the atomic radius increases with the atomic number. As we move down the group, a new energy shell is added to each succeeding element. In other words, the principal quantum number n increases down the group, and the distance between the valence electrons and the nucleus increases. As a result, the shielding provided by the electrons in the inner energy levels becomes more effective, especially if the inner orbitals preceding the valence electrons are full, as in the case of alkali metals and halogens. Therefore, the size of the atom increases down a group. According to the atomic size trends explained so far, the noble gases should have the smallest sizes, as they are the last elements in each period. However, the atomic radii of noble gases are not considered here. Noble gases, being monoatomic, have very large non-bonded radii values. Hence, the radii of noble gases should be compared with the van der Waals radii of other elements rather than the covalent radius. Van der Waals radius is half the internuclear distance between two non-bonded neighboring atoms or two adjacent atoms belonging to two neighboring molecules of an element. Van der Waals radii are usually larger than covalent or metallic radii. The radius of an atom changes when it loses or gains an electron to form an ion, and the resultant radius is called ionic radius. Ionic radii exhibit the same trend as the atomic radii. When an atom loses an electron, it forms a positive ion called cation. The radius of a cation is always smaller than its parent atom because, while the nuclear charge remains the same, the number of electrons is decreased. This results in increase in the nuclear attraction on the valence electrons, leading to decrease in the size of the atom. For example, the atomic radius of sodium atom Na is 186 picometers, whereas the ionic radius of sodium ion Na+ is 95 picometers. Similarly, when a parent atom gains an electron, it forms a negative ion or an anion. The addition of one or more electrons results in an increased magnitude of inter-electronic repulsions among the electrons and a decrease in the effective nuclear charges. Therefore, the size of an anion is larger than that of the parent atom. The atomic radius of fluorine, F, is only 64 picometers, whereas the ionic radius of fluoride ion F- negative is 136 picometers. Clearly, the variation between the atomic and ionic radius depends on the effective nuclear charge. This is why the ions belonging to isoelectronic series have different ionic radii. Isoelectronic species may be defined as atoms and ions which contain the same number of electrons but differ in nuclear charge. Within a series of isoelectronic species, as the nuclear charge increases, the force of attraction by the nucleus on the electrons also increases. As a result, ionic radii decrease. For example, N-3, O-2, F-, Na+, Mg+2 and Al+3 ions have the same number of electrons, that is 10. However, their radii would be different because of their different nuclear charges. As cation with greater positive charge has smaller radius and anion with greater negative charge has larger radius, the order of ionic radii among the isoelectronic species increases in the order as shown here. Another important physical property is ionization enthalpy. The energy required to remove the most loosely bound electron from an isolated gaseous atom X in its ground state is called ionization enthalpy. Ionization enthalpy is expressed in the units of kilojoules per mole. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. The energy required to remove the most loosely bound electron is called the first ionization enthalpy. The energy required to remove the second and the third electron is termed as the second ionization enthalpy and the third ionization enthalpy respectively. The second ionization enthalpy will always be higher than the first ionization enthalpy. This is because On removing an electron, the unipositive ion formed will have more effective nuclear charge. Due to this, the nuclear attraction on the electrons increases, and hence, more energy is required to remove an electron from the unipositive ion. The term ionization enthalpy, if not specified, is taken for the first ionization enthalpy. The graph shown here depicts the variation in first ionization enthalpies delta IH of the first 60 elements in the periodic table. As you can see from the graph, noble gases with stable NS2-NP6 configuration have the maximum first ionization enthalpies and hence are chemically inert. The alkali metals with one electron in their valence shell, on the other hand, have the lowest first ionization enthalpies and hence are highly reactive. The ionization enthalpy generally increases across the period because of the decrease in atomic size. In general, as we move from left to right in a period, successive electrons are added to the same shell. As a result of this, the nuclear charge increases while the shielding effect remains almost the same. Thus, across the period, the increasing nuclear charge outweighs the shielding effect. As a consequence, the outermost electrons are held more tightly, resulting in the decrease in size, and thus increase in ionization enthalpy across the period. However, there are a couple of exceptions to this guideline. To illustrate this, let's consider the first ionization enthalpies of the second period. The first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has a greater nuclear charge. This happens because in the case of beryllium, the 2s orbital is completely filled and moreover, the electrons are present in the more penetrating s orbital. On the other hand, in boron, the outermost electron is unpaired and is also present in the less penetrating p orbital. Hence, more energy is required to remove a 2s electron from beryllium than to remove a 2p electron from boron. The other anomaly is the smaller first ionization enthalpy of oxygen as compared to nitrogen. In the case of nitrogen, the 3 2p electrons reside in different atomic orbitals in accordance with the Hund's rule. The half-filled orbitals confer extra stability to the nitrogen atom. However, in the oxygen atom, 2 of the 4 2p electrons occupy the same 2p orbital. This results in increased electron-electron repulsion. Hence, it requires less energy to remove the 4th 2p electron from oxygen than to remove one of the 2p electron from the stable half-filled nitrogen atom. Let's now discuss the variation of ionization enthalpy down the group. As we go down a group, although the nuclear charge increases, the size of an atom and the shielding effect also increases with the increase in the number of shells. Due to this, the nuclear attraction on the outermost electron is decreased. Thus, removing such an electron requires less energy, and hence ionization energy decreases down a group. Let's look at yet another important physical property: electron gain enthalpy. It is the measure of the ease with which an atom can gain an electron and form an anion. The enthalpy change during the process of addition of an electron to a neutral gaseous atom to convert it into a negative ion is defined as the electron gain enthalpy. The process of adding an electron can be either endothermic, that is, energy absorbing, or exothermic, that is, energy releasing. It is exothermic when an element reaches a more stable state by the addition of an electron. For example, halogens attain a stable noble gas electronic configuration after gaining an electron. Hence, they have very high negative electron gain enthalpy values. On the other hand, noble gas elements have large positive electron gain enthalpies. This is because, in the case of noble gases, the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. Therefore, noble gases need to absorb energy in order to gain an additional electron. The variation in electron gain enthalpy of elements in the periodic table is not as systematic as the ionization enthalpies. Generally, electron gain enthalpy becomes more negative with each successive element across a period. In other words, electron affinity increases across a period. This is because, as we move from left to right across the period, the effective nuclear charge increases and the atomic size decreases. The addition of a new electron would be easier for a smaller atom because the added electron would be closer to the positively charged nucleus. The electron gain enthalpy decreases down a group because of increase in the size of the atom, and also the added electron would be further away from the nucleus. However, there are exceptions to this rule. For example, the electron gain enthalpy of oxygen is less negative than that of the succeeding element sulfur. And the electron gain enthalpy of fluorine is less negative than that of the succeeding element chlorine. This is because oxygen and fluorine atoms are smaller in size and have strong inter-electronic repulsions. During the addition of an electron to these atoms, the electronic repulsions are overcome at the expense of some liberated energy, and hence, the overall energy liberated is less in these atoms. However, for the subsequent elements, sulfur and chlorine, the electron gets added to n is equal to 3 quantum level. At this quantum level, there is larger space available, which reduces the electron-electron repulsion, thereby making the addition of the new electron easier. Another physical property of elements in the periodic table, usually confused with electron gain enthalpy, is electronegativity. It is the ability of an atom in a chemical compound to attract shared pair of electrons towards itself. It differs from ionization enthalpy and electron gain enthalpy, as it is the property of the atom in the bonded state and not in the isolated gaseous state. Electronegativity is a qualitative term that was devised by L. Pauling for better understanding of covalent bonds and their polarity. Although electronegativity is a qualitative measure, different scales have been developed to measure it, such as Pauling scale, Mulliken-Jaffe scale, and Aldred-Rochow scale. Of these scales, the Pauling scale, named after its discoverer Linus Pauling, is the most widely used scale to measure electronegativity. Pauling assigned an arbitrary value of 4.0 to fluorine. The table shows the approximate value for the electronegativity of few elements based on the Pauling scale. The higher the difference in the electronegativity of two bonded atoms, the more is the probability of the bonding electron pair to localize around the more electronegative atom. For example, in the case of water, oxygen being more electronegative pulls the shared pair of electrons closer to itself. As a result, the hydrogen atoms in water are slightly electron deficient, whereas the oxygen is electron-rich, causing an overall dipole moment in water. Electronegativity increases across a period. The increase in electronegativity across a period is due to the increase in effective nuclear charge. Smaller atoms have high electronegativity values than the bigger atoms. The larger the size of the atom, the lesser the tendency to attract the shared pair of electrons. This is why electronegativity decreases down a group. As shown here for the group 1 elements. The noble gas elements have zero electronegativity due to the stable octet configuration in their outer shells. Non-metallic elements have stronger tendency to gain electrons. Thus, electronegativity increases with the increasing non-metallic nature of elements across a period. As the elements down a group exhibit increasing metallic nature, the electronegativity also decreases. You have learnt that the reoccurrence of similar outermost electronic configuration after certain regular intervals causes periodicity in the physical properties of elements. Now let's see how periodicity affects the chemical properties of elements. Oxidation state is one of the periodic properties of an atom. According to IUPAC, an oxidation state can be defined as a measure of the degree of oxidation of an atom in a substance. In simpler terms, it can be defined as the number of electrons that have been removed from an element called positive oxidation states, or the number of electrons that have been added to the element, called negative oxidation states. So, the oxidation state of a monoatomic ion is equal to the net charge on the ion, positive or negative. The oxidation state of any element in the uncombined form is 0. So, oxidation states are typically represented by integers that assume positive, negative, or 0 values. How do you calculate the valence or oxidation states of elements? They can be deduced from the outer electronic configurations of elements. For representative elements, it is usually equal to the number of electrons in the outermost shell and or 8 minus the number of outermost electrons. as can be seen from the table. For representative elements belonging to groups 1, 2, 13 and 14, the oxidation states shown by elements is given by the number of valence electrons. However, for groups 15 through 17, the oxidation states are given by number of electrons in the outermost shell and or 8 minus the number of valence electrons. Transition and inner transition elements exhibit variable oxidation states. Along with transition, elements also show the oxidation states of inner transition elements. Now, let's understand the role of oxidation states of individual elements during the formation of compounds. The number of atoms of each element required for compound formation depends on the oxidation states of the elements. For example, magnesium belongs to group 2 and therefore shows an oxidation state of +2, whereas oxygen belonging to group 16 has an oxidation state of -2. Therefore, one atom each of these two elements are required to form a compound. Hence, the formula of magnesium oxide will be MgO. Note that magnesium oxide is an ionic compound, where magnesium loses electrons and oxygen gains electrons. Also note that the sum of the oxidation numbers of all the atoms or ions in a neutral compound like magnesium oxide is 0. But what happens in case of covalent bonding, where elements only share electrons, not gain or lose electrons? The oxidation state exhibited by an element in a covalent bond is equivalent to the charge acquired by its atom based on its electronegativity with respect to other atoms in the compound. The more electronegative element in a compound is given a negative oxidation state, whereas the less electronegative one is given a positive oxidation state. For example, in case of chlorine oxide, oxygen has a greater electronegativity as compared to chlorine. Therefore, oxygen atom shows an oxidation state of -2, whereas the two chlorine atoms show an oxidation state of +1 each. Now, let's take the case of oxygen difluoride. Recall that fluorine is the most electronegative element on Pauling scale, and therefore has a greater electronegativity than oxygen. Therefore, when fluorine combines with oxygen, the two fluorine atoms show an oxidation state of -1 each, and oxygen shows an oxidation state of +2. Some elements always have the same oxidation state in their compounds, with few exceptions. As we move from left to right in the periodic table, the oxidation number of the elements first increases and then decreases. As explained earlier, the oxidation number in a group remains constant and depends on its generic electronic configuration. The number of oxidation states, however, is the individual property of each group. You can observe periodic trends in the oxidation states of elements based on the formulas of their compounds, with hydrogen and oxygen. As true for oxidation states, all the elements in a group of periodic table show similar chemical properties. However, the elements in the second period do not share many periodic trends with their other group members. These elements include lithium in group 1, beryllium in group 2, and boron to fluorine in groups 13 to 17. Lithium in group 1 forms covalent compounds unlike other alkali metals that primarily forms ionic compounds. The behavior of lithium is more similar to the second element of group 2, magnesium. Similarly, beryllium behaves more like aluminium, which is placed in the third period and group 13. This similarity in properties found amongst the elements that exist diagonally to each other in the periodic table is called diagonal relationship. This anomalous behavior of second period of elements is because of three main reasons. 1. Small size. 2. Large charge to radius ratio. And 3. High electronegativity of elements. Small size means greater attraction between the nucleus and the valence shell electrons. So while forming compounds, the atom tends to share its electrons with other atoms, rather than losing them completely. Large charge to radius ratio means that the ion of the atom has a higher charge sitting on small-sized atom, a condition that favors covalent bonding. High electronegativity means that the atom has a higher attraction for shared electrons. This again makes covalent bonding favorable. In addition to the previous reasons, the availability of lesser valence orbitals and the peculiarity of the bonding capabilities of second period elements also contribute to their anomalous behavior. The first member of each group has only 4 valence orbitals, 1 2s and 3 2p orbitals available for bonding, whereas the second member of the groups have 9 valence orbitals, 1 3s, 3 3p and 5 3d orbitals. As a result, the maximum covalency, or the number of shareable electron pairs, of the first member of each group is 4, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. For example, boron can only form single charge ion with fluorine, whereas aluminium can form higher charged ions with fluorine. In addition, the first member of p-block elements has special bonding capabilities as compared to the other members in the group. They have a tendency to form multiple bonds, as in the case of carbon and nitrogen, and to other second period elements compared to subsequent members of the same group.